Hey everyone, I have enjoyed recording this video with Atri Sharma a lot and also learned about designing distributed search engine systems. I'm sure you will learn a lot as well. So if you like this video, please smash that like button and subscribe to this YouTube channel. Please share your feedback in the comment section so I can know what you think about the video. Thank you and enjoy this podcast. Hello everyone, welcome to the GeekNarrator podcast. I am your host Kaivalya Apte, and today we are talking about another interesting topic which is used almost daily. So search is something we always do daily, and we are so dependent on that we can't get away. We search for hotels, we search for cabs, we search for answers on Google, we search for YouTube videos. And especially for developers, search is so important that without Google search, we'll be completely ineffective. So today's episode, we are going to focus on how that works and how, from a practical standpoint, what are the trade-offs we have to make while we design or think about designing a search database. How does it work? From all three aspects. How do we store data? How do we process it? How do we make the queries faster? And how do we expose that data to the user? To do that, I want to make it not specific to a system design interview and more from a practical standpoint. Of course, it will also help you in system design, but that's not the goal. The goal is to understand how it works and at the end, give some pointers to our audience on where to look at when they want to learn more about it. To do that, I have invited someone who is practically involved in designing and writing these softwares that are leading in the industry in the search space, and he has years of experience doing that. So with that, I want to welcome Atri Sharma, who is a senior staff software engineer at Uber, and he is also Apache PMC member for Apache Lucene and Solr. And I think he is also actively contributing to Apache Pinot, which is one of my favorite real-time analytics software. So without further delay, I want to welcome Atri. And, Atri, let's start with a little bit of introduction for our audience to know more about you.
Sure. Thank you for inviting me, Kaivalya. So I'm Atri. My entire career has been based on search engine databases. I'm currently a senior staff engineer at Uber, as you mentioned, where I lead the search and real-time analytics groups in Bangalore. So, whenever you search for a ride or if you're searching for something on Uber Eats, whenever you hit something there, it goes through the system that me and my teams built. Similarly, the real-time analytics part is when you know how much time is your cab going to take, or how much time is the delivery going to take, or how many orders has the restaurant served, what is the current rating. All of the real-time aspects of it are dealt with Apache Pinot, which is another team that I lead. The third team I lead is the Flink team, which is actually more about absolute stream processing, where driver location, driver status, rider coordinates, and all the availability, speed limits, geofencing, all those real-time events stream into the system. So I lead the Bangalore group for all three of them. And yes, as you mentioned, I'm an Apache Lucene PMC member, I'm a Apache Solr PMC member, and I'm an Apache Pinot committer. So yeah, that's a bit about me. And before this, at Amazon, I was building their broad search engine. Prior to that, Microsoft, I was working on the Cosmos infrastructure, which is basically what powers the Bing search engine. So yeah, that's basically what.
Awesome. So that looks like a very extensive experience in specifically in the search and optimizing queries domain. So yeah, I also want to know a little bit about how has open source community help you in your journey, and how it has changed over the last few years.
Sure. So open source has been there for a very long time. I mean, if you look at the early endeavors of it, right from when Richard Stallman started the concept of free and open source, and free as in free speech, not as in free bear, right? So that's basically where we started. And then over the years, I think the creation of Linux, or rather the Unix, really spearheaded the entire concept of open source. In fact, you'll be surprised to know that one of the original pioneering softwares for open source for the new the new the editor, right? The new and Emacs editors, right?
Yeah.
I'm still an Emacs guy. So, and then Vim. So, I mean, it's funny that the original open source communities were actually designed around these editors, and then came in stuff like the game really changed when Apache Tomcat was released, because Tomcat was the first HTTP server which was widely used and was completely open source. Then with the subsequent formation of the Apache Software Foundation, open source got some structure. Before that, each community did its own thing, and then ASF really started guiding projects under this umbrella, started creating a process of community over code, which is what open source is all about.
Yeah.
Then simultaneously, the creation of different kind of licensing, such as the Apache license, the GNU license, the GPL, which is known as, and then LGPL. All of these licenses also started contributing to an overall democratization, but as well as to some extent corporatization of open source, right? So the open source software started becoming more enterprise ready, because one thing you will see if you read some historical aspects on open source is that like 15 years back, there was a general paradigm which said that open source software is generally inferior to software offered by enterprise companies, because open source is done by geeks in their pastime, right? So like it's like their hobby project they never completed. And in fact, when I was in college back in 2014, and I graduated in 2014, so the following 2012, I was taking a course in networking where my teacher said that TCP Shark or Wiresharks are basically useless softwares because they're open source, although they were and continue to remain the gold standard of network packet interception.
Yeah.
So now, in the last, let's say, 10 years, the concept of ASF and the concept of big data has really revolutionized the open source ecosystem. So now in today's world, you'll see many, I'll say you'll see very few companies investing in enterprise software, which is not open source, right? I mean, when we hear a use case of, hey, I have a batch analytical workload, everybody thinks of Spark, right? If I have a text processing workload, okay, Lucene, Solr, Elasticsearch, right? Real-time analytics, Druid, Pinot, Stream, Flink, right? So now these are things that hit your mind instead of saying, I don't know, something by Oracle or IBM or Teradata, right? So the entire ecosystem, the entire concept of how open source is viewed has changed. And now, because of the fact that multiple large enterprises are investing in open source, because they use open source, that's why they have to ensure that the product keeps evolving, growing, and sustaining. That's why they invest their manpower and their man hours into open source, and that is why it's now become a symbiotic relationship. Now companies like Google, Apple, Uber actively consume from the open source ecosystem, as well as contribute back, so that both gain and grow. So now it's a very different ballgame. At a personal level, I think I got into open source because I wanted to learn more about core technologies, and I really enjoyed being able to build stuff there. And now, my entire career is built on open source. So, as I said, with the advent of enterprises adopting open source, I think I've had the opportunity to first build these core platforms and then use these core platforms to power massive use cases, right? So that has really helped me change this end-to-end story of seeing how a platform is built to how a platform is used, right? So not just technically, it's also given me a lot of business acumen around how our products use, what do we need to build so that it scales at a level of an Amazon and Uber, right? And subsequently, it has done pretty well for my career, because obviously, I've been able to focus on one area. I've been able to stick to certain technologies and take them to production and see them work. So it has been pretty good for me.
Awesome. Yeah. Thanks for, sharing all the learnings you had and kind of the taking us through a journey of how open source community has developed and why more and more enterprises are now contributing to open source. So thank you. Cool. So I'm really excited for this session. So let's get started with our session. As I mentioned earlier, let's start with the basics, and then start building on top of it, and let's add more and more practical examples and how would it work. So if I have to think of a search engine, what is the anatomy? Like, how does it look like? What are the key components?
Sure. So, I'll set some context here and I'll try to make it as non-interviewee as possible, right?
Yeah.
So, search engine is an abused concept, first off. Let's get that straight, right? Because most people, when think of the term search engine, they imagine a Google, right?
Yeah.
Or a Bing or something like that, right? But what we need to understand is that Google, for example, let's focus on Google, right? Google is a type of search engine. It's a class of search engine, what we call as, there is a technical term to it. I'll not go there, but basically, it's a free form text search engine is what we call it, right?
Yeah.
So you can type anything and everything in Google, and Google will try its best to interpret your intent. So basically, if you look at any research paper that Google writes, it's always focused on the concept of user intent, right? So there, if you actually open up the hood of Google search engine, you'll find that in addition to a lot of optimizations that they've done around indexing and search and high availability and whatnot, a sizable amount of compute power goes into the concept of just understanding what the user intended by that specific query, and then decorating it with metadata. So we'll get to some specifics of it. I don't want to overwhelm your viewers by giving a lot of contextual data. Also, one thing I'll try to ensure is that I don't get into very specific domain knowledge. We'll try to keep it more realistic, but just want to set the context, right? Now, what we need to understand is that that's only one type of searching, right? For example, let's imagine Uber, right? When you search for a ride in Uber, you cannot perform this, or you're not expected to perform the same kind of queries as you do on a Google, right?
Yeah.
Or let's take an Amazon. When you search on Amazon, you're not expected to be performing the same kind of queries as you would on a Google, right? So, but they're all search engines, right? And you'd be surprised as to how much technology or how much concepts are common between these three search engines, right? So let's take these three as examples, like an Uber search engine, which is more, when we say Uber, let's talk about Uber Rides, right? So Uber Rides is focused on finding you riders, or finding you drivers, right? Amazon is focused on finding you products. Google is focused on finding information, or in technology, web pages, right?
Web pages,
all about entities we're talking about.
Yeah.
So the general concept under these search engines remains the same, but there are some semantic difference, right, that we have to talk about. However, those semantic difference typically lead to, architectural changes in terms of how the search engine itself is architected. So, for example, at Uber, without delving into much detail, for us, the problem statement is very different. We're talking about, if I talk about Uber rides, right? We're talking about latitudinal, longitudinal search in absolute real time, right? In Amazon, we're talking about product relevance. It might be okay if, let's say a new product is added and it is not reflected in a search result for the next 30 seconds. It might be fine. For Uber, it's not, because if a driver is in vicinity, we need to, give that information back. Similarly, for Google, the relevance is of super importance, right? So basically, because they are drinking from the fire hose, right? So if I have a billion web pages or a million web pages that can match your query, I need to show you the top 10 that are most relevant. So I have to find the top 10 most relevant based on whatever, and user queries, you've seen what kind of queries people find Google, right? So understanding your intent there, and then finding the top 10 out of the possible million documents and doing it in sub-second latency is their challenge. So let's dive a bit deep into what constitutes a search engine, right? So typically, again, this is a very high level, and I'm not going to talk, I'm not going to go into specifics of, let's say, what does Uber crawler, what does Amazon crawl? Let's talk about something that everybody understands, like a web crawler or like a web search engine, right?
Yeah.
So you can see my screen, right?
Yeah.
So basically, let's call this is the World Wide Web, right? Now let's just start logically analyzing how does it work, right? So the first thing is I need information, right? I need a way to be able to incrementally collect the information that is available from my source, right? Which is basically what we call the crawling system, right? And we will go a bit into detail of what each component does, but let's just say crawler, right?
Yeah.
And then basically what happens is we have something known as these pages are getting crawled, right? They basically are getting crawled and they're getting into my system. So that means I need to save them somewhere, right?
Yeah.
So now I have something as a page repository or storage, right? So the crawler basically is going to go and say, hey, the World Wide Web is going to the crawler. The crawler is going to store some stuff in the page repository, right?
Yeah.
Then simultaneously, I have something known as the indexing module, right? Now, again, different engines do it differently. Some basically, intercept, like do the indexing in real time as data is coming in from the crawler. But typically, that's not a great idea because crawlers pick up a lot of dirt, as we see, right? Especially because crawlers read the raw content from a page.
Yeah.
And because crawlers have to be lightweight, they typically do not do a lot of processing. That means whatever you are getting is unprocessed data. So you don't really want to work on top of it. So there's a layer of filtering and stuff. So let's actually make that. So I have a cleansing and enrichment layer, right? And basically it goes there, and then again I'm skipping a lot of steps. I'm just trying to make sure that we are getting to the crux of what's the matter. So there's a page repository stored, right? So then what happens is we have something known as an indexing, right? So I'll make it here. So now again, many optimizations script here, but let's say the indexing layer is able to read. And then, it's basically saying that, okay, now I am creating what are known as indices. And we'll talk about what these indices are in a second, right? So I'm creating indices, and I'm also potentially, such as do it, not do it, but it's typically a good idea. Indexing layer is creating these two components, right?
Yeah.
It's basically doing this, and it's doing this. Oops, sorry. Also doing this, right?
Yeah.
Then basically after you've done, you've gotten here, you basically are now going to, okay, before this, there are also layers involved here, the indexing layer where there's a analysis, and let's just call it the analysis layer, right? So I will talk about what the analysis layer does. So basically goes here, and then and the analysis goes and talks back to the indexing layer. So there are some semantics here. The metadata are collected, the indexes are built. Then what happens is I have something known as a query layer, right?
Yeah.
I have a query layer engine, which basically is going to talk to something known as ranking, right? Now, ranking is a very complex subject.
Yeah.
Typically, it's not done as a single step, but I'm just drawing it for readers' benefit. So, the query engine will pick from the, it will basically then push data to the ranking module. The ranking module will then basically be able to, filter results, and then I'm going to push them back to the user in either form of async results, or maybe I'm rendering them to, let's say, an API which is running to a web page,
Yeah.
right? So basically, that's what you see, right?
Yeah.
Now, yeah, this probably is not completely correct because here, right, you can get this. It's basically when you talk about the indices metadata, and then yeah, it's going to talk about the metadata. And then after that, the ranking, it's going to basically there's a retrieval layer first. It's not right. The retrieval layer actually goes and talks to your G retrieval, and then it goes to results are pumped out in whatever form and shape you want.
Yeah.
Okay. So yeah,
Sounds good.
again, a very high level of what this works, and we'll go through each of these components, understanding what they do, why they do what they do, and then we can get into details of how we scale it up, how do we achieve high resiliency, and what is it that is the future of search engines, right? So we
Yeah.
can do that later, but anything that I can help answer from till this point of time?
No, I think it makes sense. It gives like a very high level overview of what kind of components are, generally involved in making like search work. So if I see it from a perspective of, taking some common things out into the three areas that you talked about, like Google, Amazon, and Uber. So I think the World Wide Web and the crawler part, and also maybe the cleansing and enrichment layer, is kind of very specific to Google.
Right.
And then the other box I see is about, storing the raw data or the clean data, and then analyzing it, indexing it, storing the metadata and indices, is another box which is pretty common across these search engines. And then the query engine is, of course, it's common for
Right.
everything. Yeah. Okay.
That is correct. So yeah,
Sounds
that's a
good.
good idea. So what I'll do is I'll start getting into a bit of it, right?
Yeah.
So how do I start, right? So basically what happens is, you're right, the part where we talk about the crawling is extremely specific to web search engines, typically like Google, right? And the building a scalable crawler itself is a challenge because you have so much of bad data around. Then you have versus is the scale of it, right? I mean, billions and billions of pages waiting for you there.
Yeah.
And then how do you ensure that you're only capturing the delta, right? Because for the pages you've already crawled, they'll also change, right? And you cannot expect, let's say, I am maintaining a web page. Every time I change it, I cannot send an update to Google. Google has to figure out that something's changed, right? And it has to be pretty recent. Otherwise, if you lose the freshness of data, the search engine becomes irrelevant.
Yeah.
So how does Google ensure that every, let's say, few hours, it is able to get the right amount of results back and is able to maintain its freshness, both in terms of updates as well as new pages or even deletion of pages, right?
Yeah.
And remember that it's not just about crawling, it's also about updating your entire storage structure to ensure that your search results are not ranking or retrieving those web pages, right? Because your page repository is not your only source of truth, right?
Yeah.
So that's huge challenge. And then we're also talking about backlinks, you're talking about just the sheer volume of content you're getting. It's a huge challenge, right?
Yeah.
So in this world, I mean, that typically organizations build their own crawler, and designing a distributed crawler is a very different problem altogether. But you have some open source examples of how things are done. For example, a very common crawler is Apache Nutch. So Nutch and basically something known as Apache Tika, which together form a crawling layer for many web applications. So many search engines actually use Nutch and Tika together as a pair to do the crawling part for them. That's a very common pattern. So for our interested readers, I would recommend reading up on Nutch's architecture and the original research paper on which it was built. It'll give you a lot of insight on building a production level, real world crawler.
Okay.
So then once data gets in, it goes through a cleansing and enrichment layer. Now the enrichment layer is very interesting because let's say you and me search for the exact same term in Google right now, right? the exact same term, we will not get back the same results, right?
Yeah.
Even though we have fired the same thing, because this is something, Google actually is enriching data and enriching results based on a lot of contextual data, right? Static ranking is something that is common for both of us, but then our locations are different, our demographics are different, our past search results or histories are different, right? So we'll get to it. But yeah, at this layer, the enrichment is basically about augmenting what data you collect with whatever metadata you have, right? About the web page class or what the web page has been doing before or whatever, right? Maybe just for example, if I'm crawling something from Wikipedia, so I know some things about Wikipedia that I can use to augment every page that I read from Wikipedia, right? So enrichment layer basically takes care of that.
Okay.
Then those pages are basically sent to a page repository, which you can imagine it to be like a document store, right? Now then comes the indexing layer, which is the interesting part. So search engines are typically built on a set of standard index structures, right? So the key part of any search engine is its indices, right? Because without its indices, there's no way it can actually serve the kind of results it does, right? So, the most common data structure that is associated with any search engine is the inverted index and the terms dictionary, right? So it's a very simple concept. I have 1,000 documents. Cumulatively between those 1,000 documents, I have around 5,000 words, right?
Yeah.
The terms dictionary is going to maintain all those 5,000 words, which basically represent the discrete words or discrete terms in search technology that are seen across my entire corpus, which is the collection of documents that I'm processing. And the inverted index is basically it is what it's called. The inverted index basically says that for term foo, these are the documents that contain term, right? And typical inverted indexes go a step beyond because they also capture the position. For example, term foo appears in document 5 at position 17, right? Or even the frequency term foo occurs in document 5 at position 17, 19, 25, 26, and the frequency is 5, right? Something like that. So again, there are different kind of indexes that we talk about, but the inverted index is a very standard data structure that's used for serving search results, right? And then there are other indexes like quad trees, tries, KD trees, columnar store. For example, Lucene has something called doc value, which is basically a columnar store. So again, the interested reader can go through multiple examples of what these are. Any research paper or even the architecture of Apache Lucene, Apache Solr will tell you enough about it. But then basically the indexing layer comes in and gets the delta of how many documents have been ingested in the last 10 minutes, right? And typically there's not a batch operation. When the documents come into the system, they are typically pushed onto a message bus or an indexing layer where they are micro-batched and sent to the indexing engine, right? So indexing engine typically does not pull documents, it is push documents because indexing has to be a near real-time process. Again, to iterate in search engines, any search engine, doesn't really matter what you're doing, but for search engines, freshness is of utmost importance, right?
Exactly.
So the indexing layer will basically pick up your documents. It'll start creating the indexes we talked about. That will generate two components, two artifacts. First is the metadata, basically understanding what your corpus is all about. That is useful for enriching further results or even for stuff like machine learning based rankers. And the second is indexes themselves, right? The indexes that have been created are now stored in a separate storage area, right? Which is decoupled from your page repository. So now there's a very important distinction here. The page repository holds your pages, right? The actual documents. Let's talk the search terminology now. So the page repository is holding your documents, and the indices are basically indexing on top of those documents. So the indexes are not the source of truth. They're basically holding some metadata about the documents that are held in the main store, right? So that's a very important distinction. And if anybody has worked with databases, they'll understand this because databases always have this concept of something like a B-tree index or hash index, which is separate from the underlying storage, like from the actual document itself.
Makes sense.
Anything I can clear?
So I think just to summarize what you said, I think you covered very interesting and important points. So you talked about that, so there's an ingestion layer, and we want to leave that aside for now. And once that ingestion is done, we assume that the data is clean, it is enriched with all the data we want, and then it comes under our black box, which is the search engine. And then inside that, we have like the primary storage, which is the page repository. And usually, as you said, it is like a document store. We just store like data in form of documents. It is the raw data. And then we analyze it, we index it, and we create two artifacts, which is the metadata and the indices. And metadata is just data about the indices, if I'm not wrong, right?
Yes, it's just about, for example, we collect some statistics, right? How many times have, like what's the average size of documents, or what's the term frequency I've seen, or how many n-grams have I built. I mean, there's some statistics that I just use for, as I'm looking at my corpus of data, I'm learning things about it. So I'm just maintaining that for future reference.
Makes sense. And then there are indices, which helps us make our searches faster, which we'll discuss later. And then you talked about like the most commonly used index, which is the inverted index. And I think the best example to add is of a book. So book has the index on like the end pages where you have the words, and the words point to the pages that have those words. And as you also very importantly mentioned, that this is not the actual data, this is not the source of truth as it is in the book. So the book has its own text, there are chapters, and at the end the indices are stored separately. So indices are different and the actual data is different. So I think that makes a lot of sense. And so I think it makes sense so far.
So cool, glad to hear that. So then, basically then this is a high level overview. We'll get rid of this very soon and get deeper. But then the concurrent process to that is the query engine. So the query engine basically gets a query from the user. And, for simplicity, let's assume it's a pre-constructed query, like a very straightforward term query. Give me all documents that have the term foo, right? Then the query engine will basically go through and say, hey, this is the term that I care about. It will basically distribute the query to all the relevant indexes. And then each index will basically say, hey, I'm going to return the 100 most relevant results that come from me, right? So basically, let's say the query goes to 10 nodes. Each of those nodes is going to say, hey, these are the 100 most relevant results to your query. They go back to the main aggregator node, the coordinator node, and then the coordinator will basically see 1,000 results, and they'll be then ranked between each other. And then out of them, the top 100, 200, or whatever, will return back to the upper layer, right? Again, a very, very simple example of how a query runs, but overall flow remains the same, for any search engine.
Sounds good.
Yeah. So now that we have gotten here, let's get a bit deeper into oops, I don't know what's wrong. I'll try to delete this. Yeah. Let's get a bit deeper into what, how does a search engine look like? If I open up the box, right, what would I see?
Yeah.
So you typically see a bunch of things, right? You'd see a metadata store, right? Then you'd see a coordination store, like a zookeeper, right?
Yeah.
Then you see like something known as, for example, to use a Solr term, you have an overseer. Overseer is basically looking at the entire cluster's health, which node is doing what, how many nodes are alive, if node is dead, do I have, how do I fail it over, what jobs are running in the system right now, what jobs are failed, which jobs need to be retried, and all that, right? So overseer basically is responsible for the overall cluster or the state of the cluster and just ensuring housekeeping operations globally.
Yeah. Okay.
Right. Then we have a bunch of nodes, right? Now let's call them worker nodes. Right. And again, different search engines have different architectures. Some basically decouple storage and compute. Some keep storage and compute co-located for better performance. It depends, right? It completely depends on what is your overall objective? Is it cost optimization? What's your query pattern? There are many aspects involved here.
Yeah.
We will not get into that, but what I wanted to highlight was that all of those are possibilities, and they are more of distributed systems problems than search problems, right? So
Exactly.
the way you decide if a database should be, co-located or decoupled, the principles you use there are pretty much what you use to actually decide if your search engine should be decoupled or not, right? So that's not a novel problem, or that's not a specific problem search engine. It's just a distributed system in general, right?
Exactly. Yeah.
So for now, let's say we have worker nodes, and then those worker nodes are responsible for both indexing and search. Now again, some search engines, including Solr to some extent, divides worker nodes, right? Because one thing that is very common for most search engines is the competition for resources between search and indexing. Because search is CPU and memory bound, and indexing is CPU, network, and sometimes a bit memory bound as well. So basically, because these two processes are happening concurrently, they will compete for resources.
Yeah.
And if one takes over the other, the system will also suffer, right? So if indexing is too heavy, but search is not happening, then you're not giving the right experience to your customers. If indexing is not happening correctly, but your search is over dominating, then your freshness takes a hit. You have a long queue of documents just waiting to be indexed, and then once they get through, you may have a thundering herd problem. So that leads to a bunch of other problems, right?
Yeah.
The competition between search and indexing is a very typical problem faced by most search engines around.
Yeah.
So yeah, to get deeper into, so let's say we have worker nodes, and we have an API engine which is accepting requests, right? And then we have like a traffic cop responsible for ensuring that my traffic is not overwhelming the system, right?
Yeah.
So now what happens is, let's say the API engine will give you both indexing and search requests. And indexing can happen with a bunch of ways, right? So indexing, you can basically call an API with a bunch of JSON documents or XML documents or whatever documents you have. Or you can configure the ingestion layer to be reading from a specific source, right? So maybe it is crawling, or maybe it's reading from a Kafka topic or something else, right? So basically it can be either real-time ingestion, or you can basically push documents using batches or micro batches or whatever you like, using certain APIs exposed to the search engine. So then what really happens is that the API engine will basically, let's say there's an indexing request, right? Let's talk about indexing first.
Yeah.
So what will happen is there's basically it goes to traffic cop. The traffic cop says, okay, I'm going to, allow this request. And before we get there, right, let me actually move this worker and say, hey, I'm going to add another component, which is the scheduler, right? Now the scheduler basically talks to the coordination store to get the health of system, and accordingly schedules the request to one of my worker nodes. Again, I'm assuming that there's no segregation of worker nodes in the cluster. Any worker can do anything, but there are different ways of doing whatever, right?
Yeah.
So let's say this is an indexing request, right? So basically, let's just mark our request that way so that we know what we're dealing with. Right. So now the indexing request basically goes to a specific worker node. The worker node will take that indexing request and basically say, okay, what are the nodes that I need to care about, right? So there are two parts to it. So most of the systems are sharded, right? So in a non-sharded world, let's take a simple example, right?
Yeah.
Let's just say the scheduler determines that based on a partitioning key or some algorithm, the index needs to live on worker. Let's name these guys so that it's easier for us to talk about that, right?
Yeah.
Right there, I'm talking about worker 2, right? So the system says, hey, worker 2 is the one where this shard needs to be placed, right? So now the worker 2 will take those kinds of documents and then say, hey, okay, what I'm going to parse through them. I'm going to do some natural language processing techniques like stemming, maybe some analysis, and then I'm going to break down the data into indexes. Right?
Yeah.
So that's the main idea, right? You basically make those indexes, you store them locally, and you're good to go.
Yeah.
But typically systems don't work that way, right? Because then that becomes a huge scalability bottleneck. So what happens is there are again two ways of doing it. So in let's talk about this case, right? So basically the same thing happens. The worker two basically gets the job of indexing the data, but worker one has a replica, right? And this guy also has a replica, right? So now what happens is, as worker 2 is building the index, it starts replicating that index to these guys, right?
Yeah.
And again, this is like active replication, but typically systems start doing it as soon as your index starts getting built. And this is doable because of a simple fact that most search engines maintain their data in an append-only format, right? So if you open up a Lucene segment, you'll see something like, for example, you'll see something known as a segment. Within like a Lucene index, you'll see a segment. And a segment is like segment 1, then there's a segment 2, and so on, right?
Yeah.
And segments are like, there's only one segment open in memory. At any point of time, as indexes are being created, in-memory segment is getting those indices or documents or hits. And basically, whenever it hits a certain threshold, either in terms of time or in terms of size, it'll get sealed and get written to the disk, and a new in-memory segment will be open, right?
Yeah.
So
yeah.
what that allows us to do is basically, because these segments are append only, as soon as they are created and flushed to disk, they can be replicated to their subsequent replicas, right? So you can imagine that if, let's say, I'm indexing a huge set of, a huge collection of documents, I can basically create segments intermittently and start shipping them to the replicas even as my indexing is going on, right?
Yeah.
So that's one good part of a search engine, that you don't need to typically wait for the entire completion of indexing to happen before you start replicating, right?
Yeah.
So that's a very common way of scaling out search engines, right?
Yeah.
Now what happens is, let's get a bit into more on what typically happens, right? So okay, before we get there, right? So we talked about what indexing looks like. Right? Indexing is a very simple process in terms of it just builds the inverted index or the term index or whatever index we're building, right?
Yeah.
And it works on a bunch of documents, and then we talked about what an index looks like. So basically, a segment 1 contains, let's say I have 1,000 documents being indexed. So segment 1 might contain the index for documents 0 to 100. Segment 2 might contain from 100 to 200. And these need not be equisized documents, right? They can be anything. Doesn't really matter. As long as you have a schema on write, or in some cases even schema on read, you're able to index whatever terms you have, right? For example, Solr has schema on write, so you need to find the schema of a specific index before you start indexing. Some systems do not do that. They allow you to actually index all the key value pairs or all the terms that you see in the document, and only on read does the user actually map a certain field to a certain name field and then does a query, right? So it depends. But schema on read is typically more complex and lesser efficient than schema on write, but it is also more flexible in terms of what you can and what constraints you put in the indexing system.
Sounds good.
Yeah. So anything I can help clarify in the overall indexing process?
Yeah, I think we have covered like so many important points. Many of them are very common across distributed systems, and these are like common problems to solve. And some of them are, very specific to search engine problems. So I just want to kind of summarize just to validate the understanding here. So we have this is like a cluster I'm looking at. And there are like multiple types of nodes. There is coordination store. There is overseer, which is like a controller, which is kind of controlling the overall cluster and kind of the health of the cluster. And then there is metadata store, as we previously talked about. And then I see like different set of nodes. One is a bunch of workers. So workers are these nodes who are actually doing the indexing and the query processing, right? And then, as you said, it is quite important that you kind of create this isolation such that query performance is not degraded by ingestion or indexing, or vice versa. So, and I think again it boils down to the trade-off you're making. It's not always possible to just give like separate resources, because you want to make sure it is efficient. It is also cost effective. But I've seen in some of the databases that they provide this ability for the user to create this isolation. So they just tag some servers. So use it for ingestion, use it for reads. So that's a very interesting point. So I think giving that ability to the user so they can make that trade-off is a great idea, right?
Yes.
And
Yeah, that's true. And you are bang on point. Yes, many systems do that. So typically what happens is it works well for opinion systems, because what happens is, let's say I tag worker 2 as query only, right?
Yeah.
What that means is that worker 1 and worker 3, if they are indexers, then they'll have to ship the relevant part of the index to my worker 2, right? So basically they either ship it this way, or what they do is they basically have like a shared storage, right?
Yeah.
And the indexers actually are, let's say, they're actually, let me just draw this a bit better so that there's vision. So, there's indexing requests, and then the indexers are basically writing the final segments, the final indexes. Again, just to reiterate, we're not talking about the actual documents. We're only talking about the indexes right now.
Yeah.
So, they write to the shared storage. The query dude actually says, hey, you know what? I have a new query. What do? I actually go and read from the shared storage.
Yeah.
So basically, the interaction between the indexing and the query nodes happens through a shared memory space, right?
Yeah.
Shared disk space, actually.
Yeah.
So that has, again, its pros and cons, but that is a typical way of how these systems work when storage and compute are decoupled. So if you remember the original point that we're discussing, search engines have the option of either coupling the storage with compute or decoupling, right? So if you want to segregate, you have to either, you have to take the bullet and say, hey, I'm going to decouple my storage and compute, right? Again, as I said, there are some scenarios where you don't need to do that, as long as as the indexers know where to ship the segments after they're built. So, if your indexing nodes and your query nodes are aware of the partitioning scheme, then your indexers can figure out which, like for the shards that they're building, where do they belong in terms of the query world, right? So then they are able to ship that. And again, that has some implications, because then you need to have a very high network link open between your peer nodes, right? Because you cannot ship segments in near real time through the coordinator or through some central node, right? You need to be able to access every query node in the system accordingly. So then it becomes a problem. Do I create a dense network, right? Is every indexing node able to access every query node? Or do I actually bind saying that, okay, you know what, these two nodes are indexing for shard 1 and 2. These two query nodes are responsible for shard 1 and 2, so only they have a network bandwidth. But then that's complex to implement, and that does not work well with reliability and high availability, because in modern distributed systems, nodes are added and deleted all the time. So do you also change the network topology, right? Then that gets a bit hairy. The other alternative too, which is what Solr does, is basically create what we call request quotas. The request quota is a very simple concept. It says, let's say given a node's capacity, historic capacity, or the provision capacity, right? I say this node can serve 100 concurrent requests, right? And then I create a quota saying that out of that, 40 are dedicated, 40 are basically dedicated search requests, and search, and the remaining 60 are dedicated indexing, right? So now what that means is that under any scenario, the system will ensure this much guaranteed capacity to that kind of request. right?
Yeah.
And this is tweakable. So, I mean, in Solr 9, you can actually play whether you can tweak the coder dynamically and ensure that, the way the data is being processed changes, right? So let's say it also allows us to, work well
Mm-hmm.
with changing business use cases, right? So,
Yeah.
for example, let's say there's an e-commerce website that operates in the United States,
Yeah.
right? So during its daytime, it is imperative that the query performance be of the highest order, right?
Mm.
So that's why I'll increase the code and say, hey, you know what? Maximum capacity goes to search.
Mm.
But at the night time, I'm going, throughout the day, I'm going to accumulate the new products that come in.
Mm.
At night time, I'll say, hey, you know what? Now the query load is going to be low, or maybe even the queries I don't care. My focus is on getting new updates in place. That's why I bump the quota again, and say, more power to indexing, lesser power to search. So
Yeah.
that allows us to work in the same coupled like storage and compute manner, but with a way to dynamically control the allocation of resources
Mm.
at the node level, right? And then, as you rightly said, right, if you do want to do that, if you want to go even more granular, then you can basically control the allocation at the cluster level, which is basically
Yeah.
segregating nodes.
Yeah.
But it has to be done a bit carefully, because if not done correctly, it can actually lead to resource starvation, and also
Mm.
can, it can impair your ability to dynamically resize your cluster or be highly
Yeah.
relevant.
Yeah. Yeah. That makes sense. So I think so this quota concept is very interesting. So you can dynamically change the quota. That this is like who does this? Like which component is responsible for kind of quota management?
So the overseer works with the coordination store for this.
Mm-hmm.
And these quotas are then periodically read from a certain configuration, or maybe, if it's an event driven system, maybe every time the quota is updated, there's an event trace.
Mm.
The overseer will take care of it, update in the coordination store, and then the workers periodically pull their current quotas
Yeah.
from the coordination store itself. So
Yeah.
because, if for a large cluster, it's a bad idea to be pushing quotas out all the time because of the fan out.
Yeah.
But then, the overseer can update the central store,
Mm.
and workers can pull from the center store intermittently or periodically, just to ensure that they don't overrun the coordination store, but they also
Mm.
get the latest quota enabled.
Yeah, sounds good. The another interesting point that you mentioned was the immutability part, right? It is
Mhm.
so it's just append only, and you keep creating new segments, even if
That's
the existing data is changing. So that gives you a very nice ability that you don't have to wait for the indexing to complete, but you can start replicating the segments, right? And I think a lot of leading databases use this. But what is the downside of this, right? So we're just appending new data, and for things which change too often, we might be creating a lot of data. So what kind of trade-offs do we have there?
Sure, that's a great question. So yes, for append-only systems, actually, like the concept of like log search, the LSM tree, the log structure merge trees,
Yeah.
and for example, similarly for append systems, like what Lucene does. There are trade-offs in the sense that they're great because they're lock-free.
Yeah.
Writers don't block readers and whatnot, and then they allow you to scale well or replicate. There are a bunch of goodies, right? But then the biggest problem, as you mentioned, is updates. You cannot do point-in-time updates, right?
Mm.
Because segments once written are immutable.
Yeah.
So typical systems maintain the concept of tombstone. So basically, like segment 1 might have a new document insertion, but segment 3 might contain a tombstone for it, right? Then the problem is, once a read comes in, what is it going to refer to? So
Mm.
then every read has to go backwards and read through the latest segment to understand what is the visibility, right? So
Yeah.
I mean, for example, I can't just look at segment 1 and say, hey, what I'm going to surface this document, because
Mm.
segment 3 has a tombstone for it. And then segment 5 again might have inserted a document, right? So just getting the current state of a certain document requires you to scan multiple segments.
Yeah.
Also, the same document is in various states within my system, right? So if I talk about document 1, going back to example,
Yeah.
document 1 is in a certain state in segment 1, it's in a certain state in segment 3, and again in a different state in segment 5.
Mm.
but I am paying for the storage of document one thrice, right? Versus if I had like a B tree or B plus tree where I could just update it in time, or like in point, there's only one copy of it, right? It doesn't really
Yeah.
matter. So that's the biggest bottleneck of append-only systems.
Mm.
Updates become very expensive, and also
Mm.
your write amplification grows because now for one written document, I have multiple copies, right?
Yeah.
And then the data can mushroom out of hand very soon, especially in case of a very high throughput in terms of write or updates.
Yeah.
The number of segments you create can grow very large, and as I said, right, to get the history, you have like to get the latest state, you have to read the segments back in order. So the amount of data query scanning also grows, and they cumulatively lead to uh, an I/O problem, a latency problem, as well as a cost problem.
Yeah.
To solve that, there's a concept called as merge. So, most of the systems typically have a process, an asynchronous process that periodically looks at segments and says, hey, you know what, maybe beyond a certain threshold, if you have too many deleted documents, I'm going to merge you into a different segment. So let's say I
Yeah.
take segment one, segment two. The merge job will take these two segments, remove the deleted documents completely, have only one version of any live document, like looking at the latest update, and then create a new segment, right?
Mm.
So typically, it's like a GC, but
Yeah.
it also merges segments, right? The problem with segment merge is that it's a very expensive operation,
Yeah.
right? It consumes IO. It can even stop the. I mean, it can consume a lot of CPU and memory, which is hitherto available to my search and indexing, right? So, in addition to search and indexing, I have another competitor for resources.
Yeah.
So that the merge operation itself is expensive, and till the you cannot run the merge too frequently. But if you're not running the merge too frequently, then you risk having a lot of dead data around, right?
Yeah.
So this entire concept of updates and to handle updates, the entire concept of merge are the two biggest problems that are seen with append-only systems.
Yeah. Sounds good. So yeah, I mean, as you said, I think it boils down to, who takes the resources and who does not. And it depends on the trade-off that you want to make. If you want to give more resources to your queries as compared to ingestion, you can use the quota-based system. So I think I was just reading some document or looking at some video on LSM trees and why sometimes for write-heavy operations, they see some spikes because of the they are not able to flush to the level one, and then merging is taking a lot of time. So there were some quota based approach there as well. So you give more priority to the like writing operation as compared to the merge operation, but again there is a trade-off, as you said.
Yes.
With this, I want to focus on another important point that you mentioned. So there is like a like partitioning scheme. So since you are distributing data and the workload among the workers, you need to shard the data, you need to partition the data, and then it depends a lot on what kind of data you have and what is your partitioning strategy, right?
That's correct.
And that may lead to like hot partitions.
That's correct.
So
yes.
what are some like approaches to solve this problem and to not have these hot partitions? I've also heard that these hot partitions are gone away, or they are mitigated if you divide the storage and the compute layer, so you can do all these separation of the storage layer and the compute is not. So what are your thoughts on that?
Sure. That's an excellent point. So there are two strategies of dealing with hotspots, like the hot partitions, right?
Yeah.
So there are predictive hotspots and there are non-predictive hotspots. Now, what is a predictive hotspot, right? Imagine Apple releases its new iPhone tomorrow. I know that suddenly a lot of traffic is going to come to Apple products, right?
Yeah.
And it's typically not just the iPhone. Some people will search for the earlier iPhone because it's cheaper or something like that, right? So the Apple segment is going to get a lot of traffic. So that's a predictive hotspot.
Yeah.
I can basically, take some measures to mitigate that. The other is non-predictive, right? Suddenly, like, some certain segments start getting a lot of traffic, some certain starts getting a lot of traffic, and I'm not prepared for it. Then we need to have dynamic strategies to get rid of it. So before we get there, I'll answer your second question, which is basically about decoupling, right? So you're right. Decoupling of storage and compute does solve this problem, right? You basically have like a shared storage where you can read this data intermittently, and like if you have too much of pressure on a single shard, what you can say that multiple workers are going to read the same shard, right? Now the bottleneck there could be the storage, because if you are decoupling, you typically do not store the indexes on, let's say, D1, D2 nodes for a very long time, like the SSDs. So what you need to ensure is that if you have a hot shard, then it is basically evenly available in local caches or or let's say in some sort of a database cache or storage file system cache storage, something which is allows you to not go to the main source of truth all the time. That's something you have to ensure. And that's basically the biggest challenge you have there, like how many nodes are going to read that, and how frequently do compute nodes purge their cache segments. So let's say if I'm a compute node, I get an index out from the storage, how frequently am I going to delete it, because I'm not going to keep it for a long time. Right. So yes, you're right, decoupling does help there. In case of couple systems, there are a bunch of ideas. So the best way of dealing with this is to not have a static number of partitions. So if you have a dynamic partitioning mechanism where you're able to split partitions and merge partitions, right, then this actually works well, because let's say if I have a hot partition, I can basically split it and I can divide among multiple segments. So I'm basically increasing granularity of the partition so that the pressure also accordingly gets distributed, right? If you are not able to do that, then the other way is just to, again, it depends, right? Is it a case of a write hotspot or read hotspot? Read hotspots are easier to mitigate because you can just add more replicas, right? Write hotspots are harder because, writes typically go to the primary replica and then get replicated across. So the only standard way of basically being able to deal with such a scenario is to either, as I said, have dynamic partitions split the hot partition itself, or go to a leaderless replica mode where multiple replicas are able to accept writes with the same shard, but then you have a way of basically reconciling them and ensuring that conflicting writes are mitigated, because for leaderless replication models, the biggest problem is conflicting writes, right? How do you reconcile situations where the same object has been modified in different ways on two different leaders for the same shard, right? So then you have ways that you have like very simplistic model like last write wins, or you have models where you just show the conflict to the user and let them deal with it. Again, I'm not getting into details of that, but those are the typical ways how you deal with hot shards. The leaders mode is typically not used because it's pretty complex. Dynamic partitioning is what is generally used because you can then move on the partition or just repartition it and then buffer writes on something else. There are other ways, there are like some modern ways of doing it. For example, I forgot the term around it. It's a very interesting term, but basically what happens is that other nodes, like the nodes where your partition is not allocated to, can also accept writes for you, right? So it's basically like a lazy quorum model, where let's say a shard is under high pressure. As the other nodes that are not hosting the shard also accept writes for it and eventually buffer them and give it to it, right? So basically they handhold the hot shard to help mitigate the write pressure on it for a temporary basis. They're not taking that shard, or they're not taking parts of the shard, they're just helping it out, right? But yeah, dynamic sharding is typically a good idea because now we have concepts of virtual sharding where you have virtual key ranges distributed among a pair of nodes, and then those key ranges can move around if required, or more nodes can host the same key range. So dynamic partition becomes a lot simpler, and that is like the best way to mitigate write hotspots for a couple systems.
Yeah, sounds good. So yeah, that's another interesting point, that you need to also kind of distinguish between what kind of hotspot it is, write or read. So read, as you said, is easier because you can add more replicas. Probably you can also cache it and solve that problem. How about going back to the immutability part? just wanted to focus on another point that so you have a trade-off now that you are creating a lot more segments, and if your data is like mutating a lot, then you might have some trade-off. You have a right amplification. Does patching helps there? So it's like you have like a lot of frequent updates to a single piece of data. So instead of creating a new segment, you just patch it and then write only one value. Let's say the latest value after all the updates are made. So have you seen some techniques around that in some of the
It does work, yes. It is something that is a practice, but that only works if you are, if you know that even within your shard or your partition, the number of objects being targeted are much lesser than your overall number of objects. So let's say your shard contains 1,000 objects, and only 50 of them are being subjected to the maximum update rate. It does work.
Yeah.
But it comes with a bunch of problems because one, you're basically trading on freshness, right? So for that duration, you are actually not, you're serving stale writes, right? So that's on the first problem that you see. The second is the maintenance of those buffered writes, right? So how are you going to buffer them? Are you going to buffer them in memory? Because then if you start buffering them in memory, depending on your write rate, you actually are dealing with a lot of data, right? You basically are saying that, okay, now I'm going to buffer writes and I'm going to just consume more memory and have an additional step, in addition to my on-disk segments. The third is reliability, right? If you are buffering updates in memory, how about if your node goes down, right? Because your segments are durable, but your in memory is not, right? So are you going to, wall log it? Are you going to actually write transaction logs for in memory buffers? That increases your complexity, right? So those are the typical problems that you see, and I think that specific technique works for a narrow set of use cases where the number of objects being targeted is limited. So I don't think it's a very popular strategy, but yes, it does exist.
Okay, sounds good. Cool. So let's move on to see how this indexing works, right? So so we said that workers are responsible for querying and also the indexing part. So where are these indexes stored? Is it only in memory, or they are also flushed on disk?
Oh, so they are flushed to disk, right? So again, if they are decoupled, then they are definitely flushed to the shared storage or whichever node is responsible for hosting the shard. But if it's a coupled system, then it is flushed to the local disk, and also, as I said, it's replicated to the host hosting the replica for that specific shard, right? And typically, most systems actually employ a tiering mechanism where your latest shards live on your worker nodes for a certain duration. Then they move to worker nodes with cheaper storage and slower storage like HDDs. And then eventually they move to, like, they're compacted and they move to a cold storage system like an S3 or HDFS. So that happens through an aging policy, or like so Elasticsearch calls it index lifecycle management. And that's how typically indexes are stored within the ecosystem of a search system.
Yeah, awesome. Yeah, that sounds like a very good strategy, which gives you cost effectiveness. You don't want to store all the indexes, even if they are old. So I think the control is again given to the user, because they want to decide how long of a data I want to store in, like so-called hot storage versus cold storage. And that is a strategy I think a lot of systems are using. Great. So where do we go next? So
Yeah, I think we've talked about indexing, we've talked about merge, we talked about partitioning. I think the only remaining aspect now is querying. So querying is relatively straightforward, I would say, in the sense that what querying really does is you have a bunch of worker nodes again, right? And the query comes in, the API engine, the router and whatnot, but then the router basically throws the query to one node, right?
Yeah.
This node now becomes my coordinator for the specific query, right?
Yeah.
So in the CI system, any worker node can become a coordinator, and is typically the coordinator for multiple queries at any given point of time.
Yeah.
So then, the three operations that are most typical for a worker node in a system are: one, indexing; two, being the coordinator for a specific set of queries; and three, serving queries or subqueries asked for by other coordinators. So for basically participating in queries for which we are not a coordinator, right? But we are participating because we host a shard.
Yeah.
So then, the coordinator basically takes a query and then fans it out to all the other workers. Now, here's the interesting part, right? Unlike a database, a search engine cannot rely on pure sharding alone to prune away shards, right? So, for example, let's say, in a database, I have a field called foo, which is a
Yeah.
numeric field,
Yeah.
and I've used that as my partitioning key, right? And now I get a query on foo which says that give me all the rows where foo is less than 5. Now, based on that, I can actually determine which shards are going to host data for this specific query, and I'm not even going to touch the other shards.
Yeah.
But that is typically not how search engines work, because for search engines, you get a query, give me all the documents most relevant to my query. Now, any shard could be hosting a relevant document, right?
Yeah.
Then one of the biggest differences in terms of execution for a search engine and a database is the fact that search engines have a much higher fan out. So for a given specific query, as you can see, like for the coordinator node basically sent the subquery to both the workers, right? Because it wanted all the documents to be ranked and be given an opportunity to be a part of the top 100 of how many results we want, right?
Yeah.
Again, there are ways to avoid that, because you can basically either have, like, let's say, a specific term in the query which allows you to prune away partitions, or you can prune them away yourself by augmenting the query, right? For example, let's say you fire a query, right? You fire a generic query that you want results for, but the system knows that you're based in Germany. So I'm going to now show you results that are relevant only for Germany, right? I'm not going to hit the shards that host data for India, right?
Yeah.
Even though you did not specify a partition pruning mechanism, system figured out a known, or maybe it'll take your historical context, or maybe it'll say, okay, you search for Apple, so I have term sharding in place where I have shards created on different terms,
Yeah.
or regions created in different terms. So let's say you search for a Apple mobile phone. So I'm first going to go to the shard set that hosts mobile phones. Within that, I'm going to go to the term sets, the shards that hold the term or are associated with the term Apple, right? So implicitly, I can use these techniques to prune away partitions. But unlike databases, there is no defined way, or there's no defined key of being able to prune away partitions, saying that, hey, these documents are not going to match my query at all. Because in a search engine, any document can match any query based on relevance.
Yeah.
So that's one of the typical problems that search engines see. And then let's say the coordinator will basically fire the query to the worker. The worker will basically get the most relevant documents for the given query and return them back to the coordinator. The coordinator will then do a second pass relevance, where it will basically get the best of the best and return them back to the upper layers, which are the API or whatever.
Yeah.
So that's like a very rudimentary way of query execution within a search engine. One of the biggest things we haven't talked about is ranking, because ranking typically is a multi-phase operation. So like there's a first pass ranker where you use like a static rank to just eliminate documents on the fly. Like for example, I'm only going to look at documents which have a static rank of at least 100 or whatever, right? And static rank is typically computed in index time. Then post that, I'm going to apply a second phase ranker, which is like a TF-IDF, like a term frequency inverse document frequency.
Yeah.
There might be first phase ranker, which is actually like a neural network, which is going to only look at the results from phase 2 and say, now I'm going to apply some complex magic and say what are our most relevant documents. So typically, like, these kind of operations where you have advanced ranking methodologies happen outside of core search engines. right? For example, Solar won't do it. You'll get like first phase, second phase results out, and then apply them on your own, and then further filter them. But like the first and second phase filtering is typically done within the ecosystem at worker nodes, and you have like a plethora of options to choose from in terms of what ranking mechanism you want to use. So you have TF-IDF, you have whatever, right? You have like vectors, you have cosine similarity, you have other methodology, like these days it's scan and search, vector search which has come into mind. So there are various ways of ranking and evaluating your documents against a given query. Once that happens, results sent back to the coordinator, and then the coordinator might actually do some post processing on it to figure out the final results. And the coordinator becomes even more important for stuff like aggregations, right?
Yeah.
So if I'm aggregating on a specific field, or if I'm faceting on a specific field, so then all the shards will send their sub results to the coordinator, and the coordinator will perform a second phase aggregation to get the final result and then give it back. So imagine like if I am calculating the sum of a specific field, right? So all the worker nodes will return the sum of that field from their independent shards. And then the worker will basically do a sum of those sums and give it back, like a very rudimentary example again. So the coordinator becomes very important, but also becomes a single point of bottleneck in terms of query execution.
Yeah.
But yeah, that's typically how a query will traverse throughout, throughout the cluster just to serve its requests. The other thing to understand here is that workers will deal with either the index or the document itself. So typically they deal with the index, and they actually return a unique UUID associated with a document system, right? So basically, let's say the worker 1 returns 10 UUIDs, worker 2 returns another 10 UUIDs. Then the coordinator worker node will actually merge them and get the best UUIDs, and only for UUIDs that are finally selected will the actual document be retrieved from the document store. So remember that we are still dealing with indexes, we're not dealing with documents yet.
Yeah.
So once we figure out that these are the UIDs that are final, the coordinator may actually fetch the results and send them back. And in many scenarios, the coordinator does not do that. It only returns the final set of UIDs. The upper layers, like the final rendering layers, actually get the document from document store based on those UIDs and then perform the final operation. But till above the coordinator layer, we are only dealing in terms of document IDs.
Sounds very good. Yeah. So I think so querying still looks way simpler as compared to the indexing part, the pre-processing part, and that looks like it is the meat of the search engine. And the way or the better you organize your data before you query, it makes a lot of difference. But I think you mentioned few points here, which is the ranking part, and I'm guessing it is more relevant to the Google type of search engine, or it is also relevant for other ones.
So it is relevant for a lot of things, right? For example, for product search, like Amazon, right? If I search for Nike shoes, right? Which shoes am I talking about? If I'm just search for shoes for men, what am I talking about, right? You do get results in a certain order when you search for something on Amazon, right? So that is ranking. In fact, Amazon needs a lot of ranking because multiple products can be relevant to what you're searching for, right? Similarly, for a system like Uber Eats, right? If you search for tacos, what am I going to show you, right? Which restaurants are you most likely to order from? Because if I show you restaurants which are not very relevant, then you won't order, right? So the probability of ordering is directly proportional to how relevant the top results are. So Uber Eats has a relevance problem, right? So I mean, not problem. It has a relevance challenge to solve, which it does. So interestingly, relevance is generally perceived to be most relevant to like web search engines like Google, but it's not. I think relevance is a very pertinent problem to any system that has multiple candidates to rank between, and wishes to show results to the user that are most likely to generate a positive outcome.
Yeah, makes sense. So it is definitely relevant. But I think if, let's say I'm talking about, let's say Amazon filtering, or let's say give me all the products that are less than 10,000 rupees or something. So that is not exactly a search query, right? It's like a regular database. Yeah,
that's a more of a filter query. And you brought up a good point, because most search engines also support what is known as a filter query. right? So filter query is basically not a ranking query, does not participate in ranking. It does what you just described. It uses a predicate or a bunch of predicates to filter documents on certain criteria. And search engines have many kind of indices that are aimed at solving filter queries. For example, Lucene has an index called a KD tree, which allows you to do efficient range indexing, right? So now range indexing is, let's say you say, hey, give me all the restaurants that serve tacos within 50 miles from my location.
Yeah.
So now I have a range query which is going to get served first, which is a filter query. And then once the filter query runs and gives me such a set of candidate documents, or then basically I'm going to rank them based on, like you said, tacos. Or the other way around, I rank tacos and then I filter queries, but that doesn't really have. Filter queries are used to reduce the number of documents that go to a ranking phase, because ranking phase is expensive.
Yeah.
So yes, most search engines support this concept of filter queries, which are not rank queries, which are basically just predicates that are used to filter out documents, which work for the cases that you described. And even optimizing them is a priority for most search engines, and that has led to like the creation of multiple indexes which are only used for filter queries. So yeah, that is an active problem.
Yeah, makes sense. And another important point you mentioned was these workers are never dealing with the actual page store or the repository, right? They always work with indexes.
Yes.
So, and then there is another layer which takes all the UUIDs or the IDs for pages that have the results, and then they get it from the page repository and show it to the user. What happens when, let's say, the indexing is going on with a bit of problem? So it's slow. So there's a huge, let's say, spike of events or pages that are coming up, and our workers are not able to catch up with the indexing process. So do they still not give those results, or there are some implementations where they can directly kind of work with the page repository and still give some results which might impact the query performance? But
interacting with page repository is a bit of a mess because it's like a document store, right? So
yeah,
doing a text search on a non-indexed document is extremely slow.
Yeah.
How these systems deal with such problems is by maintaining a live index. So when I say a live index, basically what happens is that any new updates actually go to an in-memory store, like in-memory index, right? And they will be kept there for a certain duration of time till my on-disk index is available. So for example, if you look at Apache Pinot, right? Pinot has this concept of real-time text index as well as an on-disk text index. So when you have an update coming in, it goes to the in-memory text index first. So it's a fully functional text index, but it is in-memory. So that typically is a much faster process than actually building the on-disk segment, right? So while the on-disk segment is being built for a given set of updates, the in-memory index is responsible for serving those queries. So now most of these engines have a smart query mechanism where they're able to query both the live index or the in-memory index as well as the on-disk index and combine results there, right? So the results that you see is a combination of both what the live index said as well as the on-disk index is said. So in that scenario, it is, these kind of indexing problems are mitigated because you have an in-memory index that is serving results. So even though your on-disk indexing system is having a bit of an issue, there, you won't really have a relevance problem or a document problem because in-memory index is able to solve that. Again, there are problems because the in-memory index becomes very large. It becomes another bottleneck. How do you maintain reliability? What happens if it goes down? Typical problems of any in-memory system. But yes, this is a way in which you can mitigate this specific problem.
Yeah.
In terms of interacting directly with the page repository, as I said, right, it's not going to be very fruitful because unless the page repository itself is creating indexes of its own on what terms are coming in, a raw text search is going to be pretty inefficient, and that typically will not scale well from a latency perspective.
Yeah, that makes sense. Cool. Sounds good. So I think if you don't have anything to add more here, I would like to focus on the the operational aspects of these search engines. what happens when something goes wrong. So what happens when the overseer goes wrong, for example?
Mm-hmm. Yeah, see, the overseer goes, I mean, overseer is typically not a single node. It always has at least one active standby,
Yeah.
which is because the overseer is designed to be a stateless system, right? So, I mean, it basically can seed itself up from by getting checkpoints from the coordination store, the metadata store.
Yeah.
So if the overseer goes down, there's an active standby that takes over immediately and seeds itself from the coordination store and gets up to speed. And then there's another backup that's created, like it's active standby, right? So
Yeah.
all of these services are typically multi-tenant, so that they have at least one more copy available, which might or might not be serving requests, but it is there, right? And in terms of resiliency of workers or high availability of workers, replicas work well there because you always have replicas. If worker goes down, you can route queries with other replicas.
Yeah.
For indexing, we don't typically acknowledge back writes until the data is replicated at least to one more replica successfully, right? So, I mean, in some cases, a quorum of replicas for lower levels of consistency, but at least one more replica which has to acknowledge back that it has accepted a write.
Yeah.
So, in case the primary replica for a shard goes down, you can promote the other one to primary, and things keep working well.
Yeah.
So yeah, that's that. The coordination store and the metadata store are typically, like, for example, Zookeeper has its own resiliency model. The router is again a set of nodes managed by a load balancer, which is good both for resiliency as well as high throughput. So yeah, that's how these systems typically maintain a high degree of resiliency. And in extreme cases, you even have blue-green clusters where you have you have double indexing or you have replication happening across data centers. So if everything goes wrong, you can just switch over the data center, and what happens is periodically indices are snapshotted and the backups and snapshots are uploaded to a central store like S3, so that if required, you can basically, in terms of, because one of the biggest problems you see with any sort of system is index corruption. So index gets corrupted, you can basically either start working with the replica, or you can basically restore it from the backup, or periodically the replicas are also the backups are also being used to check data as to how is the data on the disk equivalent to what was taken earlier, right?
Yeah.
Also, in some scenarios, those backups and snapshots are used to seed another backup cluster, but that's typically very cost prohibitive and works only for very critical use cases, but that also happens.
Yeah, awesome. So I think this design is like typically very fault tolerance because we have redundancy, we have replicas. What happens when there are attacks? So I think you mentioned briefly about traffic cop, but that was mainly for the ingestion. What happens?
Right.
We have like a query attack or something. So do we implement rate limiting or?
Yes. Yeah, most of the systems have two levels of resiliency or defenses. One is basically at the query acceptance layer or request acceptance layer, where you basically are monitoring how many requests are coming from a certain segment, like some like user segment or area, and you basically are able to, like, network level throttling is definitely done. The other is for example, systems like rate limiters exist, so how many requests is a system going to accept, how many requests is a node going to accept. Beyond that, you might queue them, you might reject them, and then most of the systems have a concept called circuit breakers, where let's say you have configured saying that, okay, if a query takes more than this much amount of memory, kill it, right? Or if my node is above 80% CPU, don't accept new requests. Or if my node is above 80% CPU, JVM, don't accept requests, right? If I'm above 90% CPU, start killing the longest running queries, right? So these kind of self-healing or self-defense mechanism exist in most systems, and they ensure that the overall uptime of the cluster remains high, and also ensure that a single rogue query or a malicious request is not able to take over the majority of the cluster or cause harm to actual legitimate requests and queries.
Yeah, that makes a lot of sense. I think I've also seen Pinot has a rate limiter configured, and we can just specify it in the table configuration, and
Yes.
should work. So yeah, I think rate limiting is extremely important if you want to save, like defend your system from these malicious attackers. But yeah, I think it makes sense. Anything on the query side that we might not have covered, uh, according to you?
I think there's a lot on query side. I mean,
Yeah,
if you look at how search query processing happens, it's a Pandora's box, right?
yeah,
Basically, we have a lot of pre-computations. We have a lot of a lot of effort goes on, as I said, pruning shorts, right?
yeah.
Just ensuring the number of documents that a query looking at is limited. And then, for example, ranking on leaves, right? A lot of effort is taken on the fact that as much ranking as possible is done on leaves so that post layers do not have to deal with it, right?
Mm,
Then even like these days we have the concept of not doing like a multi-stage execution, right? So instead of like a one phase where it is a scatter gather model, you have multi-phases of execution where partial results are computed, then reshuffled to different nodes, and then it's an iterative model of execution so that it eliminates the possibility of one single bottleneck like the coordinator, and also allows you to do more complex processing like joins. But
yeah,
I think from an initial introduction to search engines, I think that will be a bit more overwhelming
yeah,
in terms of what all options are there. But to understand those concepts, I think what we discussed today is essential, because now that you understand the motivations behind a typical query design for a search engine, you can understand, and also its limitations.
yeah,
A interested viewer can basically understand what the modern systems are doing, and then they'll be able to map the solutions that they are using to the problems that we've discussed today. So yeah, at an essential viewpoint, this is like how typical queries work. But again, as I mentioned in the beginning, this is a very high level or a rudimentary approach, and
yeah,
there are multiple optimizations that are done, many of which are specific to specific use cases being solved by different companies or different groups.
yeah.
But I think that's a session for another day.
Yeah, awesome. So I think we have discussed, as you said, like very important points and different trade-offs that are typically made. But of course, we cannot cover like every detail because it's such a huge topic and it will take like days to cover that. Just one last thing I want to leave our audience with is your practical experience with the typical bottlenecks when we are managing such a system at production level. What are typical bottlenecks that are that are observed?
I think scalability is always the biggest challenge, right? I mean,
Hmm.
just keeping up with the rate of querying and ingestion is always a challenge, right? It is something that we constantly struggle with. And in managing a real-time proxional search engine, cost becomes an essential factor, because as you can see, right,
Yeah.
there is a right amplification involved with indexes. So
Mm.
we have to be cognizant of not adding too many replicas or not taking too many snapshots, because they add exponentially to the cost. For example, we can't do a blue-green cluster in a different environment all the time, because
Yeah.
that's prohibitively expensive. So remaining within cost constraints and dealing with a very high queue piece of both read and write is an interesting challenge. The other problem that we
Mm.
actively see is spikes, right? So
Mm.
unexpected spikes in both read and write traffic are pretty common, and your system needs to be resilient enough to be able to handle them without requiring manual intervention, because you just don't have enough time there.
Yeah.
So those spikes are ever happening and they're always present in the system, and then we have to be cognizant of that.
Yeah.
The third problem I've seen is just Murphy's Law, right? What can go wrong will go wrong. So we have
Yeah.
nodes going down all the time. We have bad deployments. We have
Mm.
bugs. How do you deal with bugs there? How do you deal with relevance problems? How do you deal with index corruptions? How do you deal with indexing backlogs? How do you will just, yes, overseer going down is a very common problem altogether. So just all of those operational aspects are very common, just distributed system thingy,
System.
and a lot of automation and monitoring around it is essential to ensure that you continue providing a holistic experience to your user. At the same time, you are made aware of the problem in the systems that with the your mean time to engage should be very minimal, and your system should be as auto healing as possible. So without
Mm.
requiring manual intervention and requiring people to move indexes, it should be able to recover and be able to continue serving requests, even if in a degraded fashion, for as long as possible while you mitigate the actual problem.
Awesome. So I think that as you rightly said, uh, there are so many things that can go wrong, but I mean, these are practical bottlenecks that you have seen. I've also seen some like spike related issues, like scalability is always a problem. So I think the concept that we discussed, like having rate limitation, or if you have, let's say, if you predict something that this is going to spike, for example, like an Apple launch or something, it's better to like scale, pre-scale your application and be ready for it. But there are some spikes that are like unknown or just unpredictable, and for that some defense mechanisms like circuit breakers and rate limited are very essential. So I think we have covered a lot, and I think this will add a lot of value for people who want to start exploring the search engine space, and just like a food for thought, so they can gather more details searching on the internet. There are so many resources, but are there some specific resources that you would suggest to look at?
Sure. I think I strongly believe in looking at reference architectures. So, if you look at, let's say, the architecture of Solr, Elasticsearch, or, many companies like Google has a paper on its overall blog system, or, how Uber has multiple blogs on how our search is designed, and even Product Search has, like the Amazon Product Search Group has multiple articles on how they did a massive migration a couple of years back. So
Mm,
just looking at those reference architectures is a good point to understand what these proxional systems look like to
yeah,
some extent.
yeah,
And then also, if you were, really want to go theoretical, I think the Stanford Information Retrieval book, or the Ricardo Besayat's book on information retrieval. And there's a book called Managing Gigabytes, which is the de facto on building search engines, are essential reads, but with a fair bit of warning, they're pretty deep and require a lot of time.
yeah.
So yeah, that they are actually for the interested reader, but they will give you a lot of context, not just on search engines, but also on ranking, retrieval, machine learning, um, things like nearest neighbor, and even some natural language processing techniques. So they are excellent reads, but they require time.
Awesome. Yeah, so I'll try to add all these resources in the the description so people can take a look at it. And these are great recommendation. I also try to look at reference architecture. So yes, I think we have covered a lot, and I thank you so much for being on the podcast and sharing all the knowledge and experience you have. And I think I have learned a lot talking to you, and I'm sure our viewers will also learn and at least be curious about search engines and the technologies that we have. So thank you so much.
Thank you for having me. I really enjoyed talking about what I really love doing, and it's been great interacting with you. You're an excellent host, very knowledgeable. So thank you for having me, and yeah, hoping this adds value to the viewers of the channel.
Thank you so much.